Here's an interesting question involving a car chase. We've got a car going at 24 meters per second and a trooper that starts out, so the initial trooper is 0 meters per second. The car is just going at a constant speed. The trooper is hiding behind a billboard, and the moment that the car passes the billboard, the trooper starts accelerating at 3 meters per second squared. We need to find the time when the trooper catches up, and we need to find the velocity when the trooper catches up. How do we do that? We need to find where they catch up, or when the trooper catches up to the car. What does that mean about each of their positions? The positions should be the same. At that particular time, the position of the car should be the same as the position of the trooper. In effect, their final positions, their x finals, should be the same. But their x initials are already the same, and so really we're just looking for when the delta x is the same. So we can write that down. Delta x car is equal to delta x trooper. They're at the same location. Well, let's copy down what equation we should use for delta x car and delta x trooper. What do you think that should be? What equation do you think we should use to express the change in position of the car and the trooper? Yeah, let's use this one. Delta x car is v naught t plus 1/2 at squared. This is a pretty popular equation because it just has so many things in it. Okay, well, we need to know when this is equal to that, so we can't really do anything with this. V naught for the car is going to be 24. T, well, we're looking for that, plus 1/2, what is A for the car? The car is not accelerating, so this is all going to go to 0. So the position of the car, the change in position of the car is just going to be 24 times t. 24 times t. What about for the trooper? Well, we can use that same equation, but just change our input variables. What was the initial velocity of the trooper? Yeah, 0. Acceleration, 3. So we plug that in, we get 1/2 there times 3 times t squared. Delta x trooper. Then we can say, well, delta x car is 24t, plug that in there. Delta x trooper is 1/2 times 3 times t squared, we'll plug that in there. And we'll get that. 24t plus 1/2 times 3 times t squared, we can cancel out the t, and then solve, and we end up getting that the time must be 16 seconds. The trooper will catch up to the car 16 seconds after the chase begins. What about the velocity? Well, we've got an easy equation for velocities. It's v final is equal to v initial plus at. If we plug in the time and the acceleration of the trooper and the initial velocity of the trooper, which is 0, then 0 plus 3 times 16 is 48 meters per second, which is actually exactly twice the velocity of the car. Interesting to me, I guess. If the trooper just keeps accelerating, he's actually going to fly on past the car once he catches up to it. Here's an alternate version of the car chase example. What if the trooper does not have instantaneous reaction times, and the trooper actually waits 1 second to start chasing after the car? How do we do this? Well, we can ask ourselves, how far does the car go in 1 second? Well, its speed is 24 meters per second, so presumably it goes 24 meters in that 1 second. If we start our timer, let's say that we have a stopwatch or something, and we start that stopwatch the moment that the trooper starts moving, then the initial position of the car is not 0, it's 24 meters. The car starts off at 24 meters. If we start the timer at the moment that the trooper starts moving 1 second after the car passes by. Okay, what can we do with x initial? We don't have any equations with x initial in them, but we do know that the change in position of an object is equal to the final position minus the initial position. Delta anything is final minus initial. So we can change the delta x's to be that. We would then need the final positions to be the same. When the final position of the car is equal to the final position of the trooper, then the trooper has caught up with the car at whatever time that is. So let's look at this, and let's start converting our equations. We'll use this equation again. We'll just plug in this in for there. So for the car, x final is what we're looking for. X initial is going to be 24 meters. Acceleration was 0. We can also move some things around. I show here that I've just taken this minus x initial, added minus x initial to both sides, or added x initial to both sides. That got it over there. A lot of you will actually probably be more familiar with this formulation of the equation right there from high school, that x final is equal to x initial plus v naught t plus 1/2 at squared. It is the exact same thing as this equation. I've just replaced delta x with x final minus x initial, and then added x initial to both sides to get it over there. The equations do the exact same thing. Use either one that you want, just know what you're doing. Okay, we can do this the exact same way we did it before, recognizing that the x finals need to be the same. So over here, we've got x final car, and over here we're going to have x final trooper. X final car, well, we've got this extra x initial there, and that was 24 plus 24t there, and then x final for the trooper, there's none of that going on, so it's just 1/2 times 3 times t squared. And now you have to do the quadratic formula. You can get all the things onto one side equaling 0, and the quadratic formula, which never looks pretty, but most people have a calculator that can do it automatically, and you can figure out the two possible answers from that. Two possible answers are 16.94 seconds or negative 9.44 seconds, or 0.944 seconds. Which one do you think is more reasonable? I think that the trooper will probably catch up to the car after the car passes by, and so we should probably have a positive number in there. This number actually indicates the moment that the car passed by the trooper, because remember, we're starting the timer at the moment that the trooper starts moving. So before the trooper started moving, the car had to pass by. This makes some assumptions about how the trooper was accelerating, which end up not being quite accurate. So generally you can just ignore that negative time right there.